I'm going to introduce Team 7. Our project is titled Neutron-Based Isotope Production, MO99 and Plutonium-238. Our researchers go from left to right in our photo and the three below. And without further ado, let's jump right into it.
Isotope production is crucial for making radionuclides that do not occur naturally in useful amounts but are needed for modern technology. This report focuses on two such products of neutron irradiation, Pu-238 and MO99. Both are made in high-flux research reactors where neutron capture and fission reactions turn target materials into useful isotopes. This report reviews the nuclear reactions involved, historical development, key facilities and contributors, and the engineering and supply chain challenges that shape today's Pu-238 and MO99 availability for space exploration and nuclear medicine. This project aims to explain the theory of neutron-induced reactions used to produce Pu-238 and MO99, review key experiments and major scientific contributors who shaped their development, and connect these ideas to nuclear 300 concepts. Plutonium-238 is a man-made radioactive isotope that undergoes alpha decay and produces steady heat, making it ideal for powering long-duration space missions. First produced at Savannah River in 1959 and used in the Transit 4A satellite in 1961, Pu-238 has since fueled many radioisotope thermoelectric generators. But U.S. production stopped in the late 1980s, leading to a supply shortage until Congress directed DOE and national labs to restart production. Because Pu-238 does not occur naturally in useful amounts, it must be made by neutron irradiation, so its availability and the ability to power deep space missions depends directly on neutron-based isotope production.
Molybdenum-99 or MO99 is also a man-made isotope that gained a lot of importance around the 1960s when it began to be used in medical applications. It's usually produced via the neutron-induced fission of uranium, where highly enriched uranium used to be preferred, but after a couple of reactor shutdowns around 2010, low-enriched uranium was deemed to be a safer alternative. The main use of MO99 boils down to a temporary active storage of technetium-99m. This is mainly due to the short half-life of the two isotopes of 66 and 6 hours respectively. Technetium-99m is one of its daughter isotopes that is currently responsible for around 80% of all nuclear medicine diagnostic procedures.
For this section, I'll start with the theory behind neutron-based isotope production, and then we'll connect that to the experiments performed on the isotope and the data that supports the said behavior. So, neutron-based isotope is typically when a stable nucleus absorbs one or more neutrons and becomes radioactive. This can happen through neutron capture, which is where the nucleus absorbs a neutron and becomes radioactive, or it can happen through neutron-induced fission, which is important for isotopes like Mobilium-99 that come directly from the fission of uranium-235. So, there's many nuclear parameters that we'll need to see whether these reactions occur. One of the most important is neutron flux, shown as phi, which measures how many neutrons pass through a unit area per second. Another key quantity is microscopic cross-section sigma, which expresses the probability that a neutron will interact with the nucleus. We then have the decay constant lambda and number of target atoms n. All these parameters come together in the standard activation equation shown here, which predicts the activity built up during radiation. The equation also shows that as time increases, the activity approaches saturation, which means that the production rates and the decay rates end up balancing out. And on the right over here, the figure illustrates how capture cross-sections vary with neutron energy for different nuclides. This demonstrates why neutron's energy spectrum matters. Some isotopes have much higher capture probabilities in thermal ranges, while others interact more at fast energies. Understanding this behavior is essential to choosing reactor positions or designing targets for isotope production. Starting with the people who built the foundation for neutron-based isotope production. Enrico Fermi built Chicago Pile 1 in 1942, the first controlled nuclear chain reaction. This proved we could maintain a steady neutron flux, which is the key to producing isotopes in reactors. Leo Szilard developed the early theory of neutron chain reactions in the 1930s. His work explained how neutrons multiply and how to control a reaction, basically core reactor physics. And Glenn Seaborg identified NP237 in 1940 and Pu238 in 1941. He also mapped the actinide chemistry that modern Pu238 production still depends on. So these three gave us the physics and chemistry that everything else is built on, essentially. Moving forward in time, here are the researchers who turned early theory into practical large-scale applications. R.E. Boyd worked in the 1970s and 80s at the NRU reactor. He led the development of industrial-scale MO99 chemical separation, basically a process that supplied medical imaging for decades. On the medical side, Walter Tucker and Powell Richard were the researchers who invented the MO99 TC99M generator, also known as the Molly Cow design, which essentially made TC99M practical for hospitals and is still the basis of generators today. For PU-238, their work is carried out by teams at Oak Ridge and Idaho National Lab. They restarted the entire U.S. PU-238 production line after almost 30 years and developed modern methods for irradiating NP-237 targets and chemically recovering PU-238 for NASA missions. So, Boyd and the generator inventors shaped modern nuclear medicine, and both the national lab teams rebuilt the PU-238 supply chain needed for deep space power. So here's why these researchers actually matter. Their work around MO99 made TC99 imaging possible, and around 80% of their nuclear medicine procedures use TCMM that relies on and depends on MO99 production. On the space side, advancements in PU-238 production made deep space missions possible. Things like Voyager, Curiosity, and New Horizons all rely on PU-238 RTGs. And all of this ties directly back to Nuclear 300. Neutron activation, decay chains, radiochemistry, reactor physics, pretty much the same concepts we learn in class are the ones that researchers use to solve real engineering problems. So overall, these researchers took theory, turned it into technology, and made both modern medicine and deep floor exploration possible.
The goal of plutonium-238 experiments done by Oak Ridge National Laboratory and Idaho National Laboratory was to restart U.S. production of plutonium-238 for NASA RTGs after a long 30-plus year gap. The additional goal was to produce over 1.5 kilograms per year of plutonium-238 by 2025 using neutron irradiation of neptunium-237. To do this, they fabricated specific targets of neptunium oxide and aluminum ceramic pellets with engineered voids, and they used specific reactors at Oak Ridge National Laboratory and INL, the HFIR and ATR reactors. At Oak Ridge National Laboratory, the HFIR had a high flux with about 25-day cycles, where they used longer cycles and multiple flux trap positions at the ATR reactor. The nuclear reaction was specifically a 237 neptunium neutron capture to 238 neptunium before a beta decay from 238 neptunium to 238 plutonium. They wanted to optimize the plutonium-238 pathway and minimize the impurities that formed in the target to keep a high plutonium or purity of plutonium-238. The milestones came in 2015 when the first 50 grams of plutonium-238 were successfully produced at Oak Ridge National Laboratory, and in 2019-2023 the annual production scaled to about 400 to 600 grams per year. The results: a plutonium-238 purity of about 85 to 90% depending on flux and time. They were able to verify the validity of the targets that they had created, and they were able to efficiently recycle the unconverted neptunium-237. These produced isotopes were to be used in NASA's Perseverance rover, the MMRTG, and are on track to meet full production of 1.5 kilograms per year.
Across our project, we examined 5 different experiments involving the production of molybdenum-99, which has a lot of application in nuclear medical science. So I'll start sharing my screen so I can discuss these. Okay, so the first one we discussed was an experiment by Ramamurthy, which was an overview of molybdenum-99 production routes. Overall, this was less of an experiment and more of a collection and presentation of data on different ways to produce and manufacture molybdenum so that way it can eventually become technetium-99, excuse me. It highlights a lot of the issues that different manufacturing methods have. The main manufacturing methods are irradiation, which is obviously what's talked about here, accelerator-based production, and neutron capture production. This article focused mainly on the irradiation, but it highlights issues present with all of them, like the target of the uranium foils, the irradiation scheduling for just the uranium, and the irradiation measurements. It also discussed issues like supply chain reliability. Overall, they came to the conclusion that irradiation is still the most efficient and overall best way to produce molybdenum-99, but other methods are becoming more viable and have become more viable since this paper was written. The next up was the target technology experiments, which was conducted by Takas, and this focused on accelerator-based production, specifically excitation using proton irradiation of molybdenum-100 to produce either molybdenum-99 or straight into technetium-99, depending on the excitation levels of the protons. It still involved target experiments, though, because they measured and looked at different target profiles of the molybdenum-100 and different excitation levels, and compared the values and production levels of accelerator-based production at certain different target types and target angles, or not angles, different target profiles, and how they all stacked up against each other, and then overall how they stacked up against irradiation production. Next was chemical separation experiments. When producing molybdenum-99, it needs to be chemically separated from the other fission products that are produced. So in the FRM2 article that we found about molybdenum-99 production and waste production, they discussed acidic and alkaline methods of separation. Acidic is generally used more for lower enriched content, and alkaline is used for higher enriched uranium targets, but they discussed nitrogen trifluoride plasma, which is a different alternative to separate molybdenum and also really reduces radioactive waste produced during the separation. The next experiment was a generator or Molly-Cow experiment. This is the process that actually brings out just the molybdenum that can then decay into the technetium-99. This experiment and this document was written in 1999, and it outlines kind of how they originally developed the Molly-Cow generator and how different experiments of alumnia absorption and saline elution of molybdenum-99 into technetium-99 helped develop and ensure and kind of confirm that they were doing the Molly-Cow correctly. Lastly, we focused on the reactor system experiments, specifically the BR2 reactor flux trap and core modeling experiments. These experiments showed that accurate flux mapping and core modeling is essential to optimizing target placement. Or no, they help optimize target placement. They can predict fission yields easily for molybdenum-99 and overall are very essential to making sure that you have not only an abundant amount of molybdenum-99, but a very pure amount of molybdenum-99. That is all the experiments that we looked at for molybdenum-99. Thank you so much.
Hi, so my name is Abby Preston. I'm going to continue our discussion of nuclear isotopes, specifically related to optimization and some comparison parameters. So parameters of interest for MO99 include target geometry, irradiation performance, uranium molybdenum microstructure stability, and MO99 recovery and uranium cycle processes required to convert highly enriched uranium production to low enriched based supply chains. So what does that all really mean? Essentially, since we know that MO99 is a fission product, the radiochemical separation process is the core challenge. So all of these parameters are geared towards simplifying that process. Plutonium-238 is a space isotope, and optimization right now consists of looking at ways to drive down the costs. Specifically, the most researched and most looked at method right now is looking at improving the Neptunium-237 target, looking at that fabrication process, and boosting irradiation efficiency. So by doing these things, hypothetically, you could get more plutonium-238 per target and per cycle, which would overall obviously exponentially lower the cost, which is being actively researched currently. Although it's important to note that RTGs have been used for a while. They supported missions like Voyagers 1 and 2, the Preservations rover, and New Horizons, which we can see in this diagram here. Finally, I want to highlight a few comparisons. I specifically want to look at production of scale and economic model. So production scale, MO99 is being produced weekly. and a production of kilograms, whereas plutonium-238 is operating on the gram scale. It's a multi-year campaign. NASA stated that over a decade they were able to produce about 1.5 kilograms, which did support their needs. However, it's extremely expensive, ranging $1.5 to $4 million. I also want to highlight that the economic model for these isotopes is very different. MO99 is produced by a few reactors. BR-2, HFG, these are located in Australia, the Netherlands, and Belgium, and these support the entire world. Whereas plutonium-238 is state-sponsored and it's considered a strategic national asset, means it's much more under lock and key and very specific to location. This just goes to show the difference in nuclear isotopes and how vast their applications can be, which really goes to show the breadth of nuclear engineering.
Hello. I will be talking about the radioactivity and isotope production of plutonium-238 and molybdenum-99. The first equation is the targeting of neptunium-237 with neutrons, which then transforms into neptunium-238, which then decays into plutonium-238, which is our target isotope. The equation at the bottom represents the neutron activation of molybdenum-98 into molybdenum-99. This process is also used as an alternative to uranium-235, although it produces a lesser yield. This equation represents the number of atoms of isotope 3 from a 3-isotope neutron activation chain. In this case, isotope 3 would be plutonium-238. The first term that you see represents the production rate of isotope 1 to isotope 2, which in this case would be neptunium-237 into neptunium-238. The exponential terms to the right represent the atomic losses due to fission and decay.
Although the production of both molybdenum-99 and plutonium-238 is primarily neutron-based, the concept of charged particle interactions that have been talked about in class can be applied to the decay products, as well as the concepts of shielding and photon interactions. The technetium-99m that is gained from molybdenum-99 beta decay emits gamma rays after internal electron interactions. These gamma rays are primarily used for imaging in the medical field. Plutonium-238 experiences alpha decay that requires shielding. These alphas do not have much penetrating power, but release a significant amount of heat, which requires thermal shielding, as opposed to a thick shielding needed for something like gamma rays.
This is the atomic physics relating to Nuke 300 for our topic, a regular isotope versus a neutron-based isotope. A regular isotope is simply a version of an element that has a different number of neutrons in the nucleus, while a neutron-based isotope is an isotope created through the process of neutron interactions. Both plutonium-238 and molybdenum-99 fall into this category. Plutonium-238 is created when neptunium-237 captures a neutron, becoming neptunium-238, which beta decays into plutonium-238. Molybdenum-99 is created when uranium-235 absorbs a neutron and fissions, and molybdenum-99 is one of the major fission products. Now, for the nuclear physics side, binding energy. Binding energy tells us how tightly the nucleus is held together, or in other words, how much energy is required to break it apart. Higher binding energy per nucleon generally means a more stable nucleus. This matters because of the likelihood of the neutron capture, the stability of the project nucleus, and even the decay pathways all tie directly onto how tightly bound the nucleus is. If you see in a slide, I listed the different energies for either of them, and we see with plutonium, it's a lot stronger.
This concludes our presentation. Thank you.